So calibration is a process by which we seek to estimate the values of parameters that are less well known using data that concerns emergent behavior of the system and is matched against emergent behavior of the model. Calibration is one of several techniques for drawing on empirical data to inform a model. But in contrast to parameterization, where we take that data and we place it directly into the model to estimate the value of a parameter. Maybe it's the frequency with which a case of gastrointestinal illness is reported to the healthcare system. Maybe it's something about the contact rate between two individuals, how characteristics of the network associated with intravenous drug use. These are all cases where we might have data that we can directly put into the model to inform it, or at least estimates for such data. But in other cases, the data we have from the world, the empirical data that we have, relates not to one particular parameter of the model, but rather to an result of an entangling of many portions of the model. So we think about data, for example, on incident cases of measles, or you think about data on occurrences of suicides, or you think about data on the number of discharges from a hospital. These are not the reflection. These cannot be reduced to an estimate for just one parameter in your model, typically. Rather, they result from a lot of interactions of different factors. So something like incident cases of TB might reflect, yes, something about contact patterns for TB as they existed over the past many years, but also something about reactivation rates of TB, the likelihood that a latent case of TB pops up again, particularly when immune systems are weaker. It might also involve something about the effectiveness of active identification of TB cases versus passive care seeking. So it might involve aspects of care seeking behavior of a person, and even in some cases factors involving death rates and so on, because a person who was subject to a TB case 20 years earlier might reactivate later if they didn't die from that earlier case. So here, if we have data over time on the number of TB cases, we can't directly put it into our model. It's something often that our model for a TB model will be seeking to produce endogenously. Remember, exogenous things we tell to the model in a pre-specified way. Those things we can put directly in, even if they're time series or whatever, that's fine. But the endogenous things the model is generating, we can't simply say, do this, make it this. No, rather the model has a theory, and we're trying to see if that theory is consistent with the evidence. And so we're trying to take the model and match it to that data, see the degree to which it matches. And often we do have we have parameters that relate to latent parts of our model, or less well-known parameters that relate to observable parts of our model that are hard to estimate, or where we don't have very good estimates, or where we have outdated estimates, or estimates from other populations. And calibration provides us a way of taking this data about emergent patterns that we see in the world and putting it to use in estimating model parameters, which are less well known. Okay, so here, this is occurring typically after the place where we put in initial parameter values. And we've got this model, for this version of the model, we've got it assembled, and we're trying to match its output with what we see from the world, both in the form of reference modes, of behaviors over time or over space, but also in terms of this data that we have that might be used for estimating parameters. So, this is a model for diabetes, and this is a system dynamics model, obese and non-obese and undiagnosed, pre-diabetic, diagnosed pre-diabetic. And here we might have parameters for particular values that we might try to draw from the healthcare system. And we could draw parameter estimates from many sources. These days we draw a lot from our Ethica IEPI system, the smartphone app to use to inform some administrative data, to inform other studies in the literature, other models. And, some of those, this was from Kristen Hess-Miller-Litch's great work at Michigan for her doctoral dissertation on tuberculosis and smoking and the interaction between the two. She used meta-analysis to try to arrive at parameter estimates for certain values in the model. And we've seen how we could use sensitivity analysis as captured through parameter variation experiments in AnyLogic to identify model parameters that are quite sensitive, to which the model is quite sensitive in terms of its outputs. And we might extend this further to the idea we might look at parameters particularly to which policy choices are quite sensitive. Not just is the model output over time sensitive, but is our choice between policies sensitive? But there's many cases where we don't have reliable information on some parameters, but we do have other data. And sometimes these parameters might be about portions that are not directly observable, but they relate to things that are observable. And remember we talked about yesterday, in the closing hour of our discussion yesterday, how when we have these models, these complex systems models, things are tangled together. I mean, let's go over to our model here. I mean, here if we looked at, I'm going to open up the model on which we've been working. Here we go. And within this model on which we've been working, we have a lot of different entangled factors. We have heart disease, yes. We have smoking rates, yes. We have aspects of behavioral motivation. We have aspects of care seeking, pregnancy, etc. And these are not solitudes. These are not independent of one another. These are not things which, you could have any value of one and any value of the other. They're actually coupled. They're tangled together in a certain way. And so if you have very high rates of smoking, it tells you something. It yields behavior in terms of heart disease. And, we're not in just any old state with respect to this population-wise, any old level of smoking, any old level of heart disease. No, they kind of go together. They vary together. One doesn't totally determine the other, but they vary together. And when we have portions of our model that are more observable and portions that aren't, sometimes we can have data about the portions that are, and it tells us something about the portions that aren't. Right? It implies something given the hypothesis captured in the model. To give another example, if we have data on the number of people becoming, we may not know how many people out there are pre-diabetic. We may not have great information on the number of pre-diabetics out there. Some spot studies done in an opportunistic way, perhaps in hospitals to try to sample from the population, not in hospitals, in malls. I know that were done in our town and so on. But fundamentally, there are a lot of people out there who may be undersampled, et cetera. But if we keep on seeing year after year a large number of diabetics being diagnosed, it tells us something about the number of pre-diabetics out there. Right? I mean, if there were almost no pre-diabetics out there, it would limit the flow we would expect for on a yearly basis the number of people becoming diabetic. And similarly, given the number of individuals with risk factors for prediabetes, that tells us something about the number of prediabetics. So just because we can't directly observe one piece of our system doesn't mean that we can't try to understand what the parameters governing it might be for the model to hang together. And there's basically two ways we use with modeling for dealing with these kind of data gradients, where we have some data in one area but not in another. One is a more algebraic way. When you have very defined conditions, you end up making often pretty strong assumptions about equilibrium or what have you when you derive parameter values. The other is with automated calibration, and that's the one I'm going to emphasize today. Okay, the idea here is a little bit like, at a certain level, it has some similarity to nonlinear regression, but you're not specifying a fixed model form of the model output, a fixed functional form of the model output. You're trying to get a model to match multiple time series as well, not just one dependent variable, but many things at the same time. So we're trying to take our model and account for many types of data that we see and see how well does it jive with all these types of data, not just one, but several types. To what degree is it a coherent theory that allows us to capture the patterns we see over time? And this is from a system dynamics model related to one we just saw a few minutes ago. And here we have data on diagnosed cases of stage renal disease, prevalence, type 2 diabetes, and those in the corner reported as being diabetes, or reports of individuals with type 2 diabetes. And we're trying to get the model to kind of match this data based on its theory of the world. I'm not going to go into the backing out. Suffice it to say that in certain narrow contexts, we take data, which we do have, we make some simple assumptions to try to derive what the value is that we don't have. So, suppose we know we're trying to find out sex-specific prevalence of diabetes in this population, and what we know is the breakdown of the population by sex, the fraction of each sex, the population-wide prevalence of diabetes, and the prevalence rate ratio of diabetes in men compared to women. In that case, we can kind of derive what these values must be for these to be consistent. Occasionally, we're in a situation like that. What's more like, and this is just an algebraic type of manipulation, more commonly what this involves is imposing some pretty strong assumptions of equilibrium or independence, etc. And we end up kind of squinting and saying, well, I think, let's make this assumption. Let's make the assumption that the number of pre-diabetics is not going up or down over time. So the number coming in has to equal the number going out. And so here we have these people getting diagnosed to diabetes, and you end up trying to back guess what's going on in the pre-diabetes side. The problem is that those are often pretty strong assumptions because the world typically does not oblige us by being in equilibrium. Equilibrium is not a pronounced feature in the health space for many conditions. And, we have rising rates of obesity, we have rising rates of diabetes, end-stage renal disease, or what have you, and assumptions of equilibrium are often problematic. In many cases, what we're dealing with, the types of data we're dealing with are affected by a lot of things. They're affected by mortality, they're affected by the demographics, they're affected by incidence, they are affected by migration, they're affected by a whole bunch of things that are tangled together. I mean, just look at this model we got. We got these tangled things, right? And they're not gratuitously tangled. They're tangled because things in the world are tangled together in terms of motivation and behavior change for smoking and pregnancy and transmission of norms, as well as potential sort of predispositions to addiction and heart disease and mortality. It's a messy world out there, and we can characterize aspects of that messiness with a model. And therein lies the root of the route of possible success when it comes to calibration. It's this ability to tap aspects of the model. So calibration, this process of calibration is basically a process of triangulating what might be going on with respect to a modest number of parameters based on diverse data that you do have. And it involves tuning values of less well-known parameters so that the model's output, ladies and gentlemen, the output best matches the observed data. Okay? And often here we're trying to match against many time series or pieces of data at once. It's not always time series. It may be particular discrete data points. Or it may be features of the situation, like women have higher rates than men, or the values are going up over time. It doesn't have to be point estimates. And in some cases, we don't have luxury of point estimates. What we have is broad patterns. Broad patterns. And the goal here is to get software to answer the question, what must these values of these parameters be in order to explain all these different sources of data that I do see? To explain all of these things, what gives? What do the values of these parameters need to be to explain this? And one of the key things to realize about calibration, it took me many years for this to fully sink in. It's a mistake to view calibration as just a step on the way to getting a fully functional model that we use. To say it's just a stage we go through. We've got to go through it. We grit our teeth and bear it so that we can arrive at a model that we can use for useful investigation. To arrive at a model that we can learn from, which we can learn. That is a grand mistake, because calibration often is one of the biggest nexi of learning. This is one of the biggest places where you do learn. You develop an intuition for what's possible with the model, what's not. What the data implies in terms of your theory and where it doesn't fit with your theory. Where it rubs the wrong way, where the tensions are in explaining this data. Are there different competing hypotheses that are consistent with the model depiction that would explain this data? That sort of thing you learn in calibration. That is not the route to, just a long dusty road to learning. That is the learning that a lot of the time comes with modeling. It's struggling with calibration. It's a struggle, and a struggle from which you can ensure you can return victorious and triumphant. Okay? I may be sick, but that doesn't prevent me from having flourishing of enthusiasm at points. Okay, so let's go back to this. So in fact, let's go switch over, as I am wont, to interactive exploration of this. So let's go to those two models at which we've been looking. And I would like to invite you, as I often do, to run this first model. Okay, you notice SIR-agent-based calibration, there's a thing called calibration there. Do you see that? Yeah? I'd like you to go, and I would like you to run it. Ladies and gentlemen, what we see here that lies before us is an example created by the folks at AnyLogic. And it's an example I use a lot. I'm going to go to the view area so that I can, oh, look at that. Well, okay. Well, it's being truculent, and we'll have to live within its truculence. Okay, ladies and gentlemen, I'd like you to go. So here's some data. This is historic data shown in yellow. And what's going to happen, ladies and gentlemen, is that this is empirical data, or designed to be the sort of empirical data we have, and that shows years here. And there's a model. We have a model here, which if you go poke around, you will find there's a model of a person, and the person susceptible goes through an infection phase. They're infectious. During infectious, they send messages to others that can make those others infectious, and then at some point they recover. And there's a hazard rate here that's dictating that, and a contact rate, and by which they can have risk of transmitting to others. So there's this theory that we have, and there's connectivity between people and so on. And we're going to try to match the model outputs here against this historic data while adjusting those model outputs. It's actually adjusting two model outputs that I consider not particularly desirable to adjust, but that's the way that the cookie crumbles here. My extension has a better set of model outputs. So the two outputs are here in main, or the two things that it's adjusting. One is contact rate, and the other is infection probability. Okay, so those are the things that it's adjusting. So we're going to say run calibration, and it's going to try to run this model and match it. You'll notice it's running it, and one important factoid here. Okay, now I'm in a pickle. My nice controls have disappeared. Here, I could pause. Okay. Okay. So, ladies and gentlemen, here, what we're trying to do is we're trying to run the model for different parameter values. For different values for those two parameters. Think of it as a vector of two elements. One for contact rate, one, ladies and gentlemen, for transmission probability. We're trying to run the model for each possible value, things that assigns specific values to each of those parameters. We'll run the model. But we'll run the model, in fact, ladies and gentlemen, more than once. We'll run it several times. Why do we run it several times? Why would we run the model more than once? Stochastics, ladies and gentlemen. So if we go and we look at calibration here, one of the things we'll find is that down in the replications area, it's saying to run the model 5 times per replication. What that means is for each posited value of the pair of parameters, say the contact rate 3.835 and the infection probability 0.318. For that time, it's going to run it 5 times over because those 5 might exhibit different behavior. And some of them, by fluke, perhaps, may match very well with the historic data. Others might, because of stochastics, might not match that well. And it's going to take an average of how well or how discrepant they are from that observed data, the so-called fitness function or objective function or discrepancy function. It's going to, for each run with those parameter values, for each realization, each replication, it's going to compute the value of that discrepancy function. And for each of those 5, compute it, take the average, and say, is this the best so far? If it's the best so far, it's going to show it here. It's actually going to show one of them here. And here, it's going to show the average value obtained thus far from that. So here, this is the best one it's observed thus far. This is the best one. It's getting others. I don't know, can you see these here? Yeah. These others are ones that it ran, but weren't as good as the best thus far. So it's, it's saying Okay, that's good enough, but it's saying, okay, there's others, fair enough, there's others, but it's got to run more to see if it can do better than this. So you'll notice it's already matching pretty well, pretty decently with the one that's shown here. These blue are showing different particular realizations, different particular replications. And, it found another better one yet. So it's homing in, zeroing in on sort of a value for the parameters that exhibit the best match, that minimize the discrepancy. This, ladies and gentlemen, is an optimization type context. We are optimizing these two parameters such that the match to the model is model results with empirical data as close as possible. Now, what results from that is not necessarily a correct value for the parameters. After all, it depends on what's elsewhere in the model, so it's contingent on the model. But at least it may give us a plausible set of values for those parameters given our other assumptions about model structure, conditional on model structure. So here we're adjusting this, and we're basically saying, okay, we will run a certain number of runs. So here we're running 500. Do you see that? 500 runs. Now, let's take a look at how this is implemented. The good news is, ladies and gentlemen, that your understanding from parameter variation will carry over very well here. Let me highlight some essential similarities between those. Calibration, like parameter variation experiment, involves a situation where we have run one experiment running the model many, many times. In both cases, when it runs the model, it is often varying parameter values. Remember we saw that for parameter variation experiment? We could systematically change the values of the parameters. Do you remember doing that? We actually ended up doing finally a one-way. Do you remember this? Varying parameters here? And we actually did a two-way parameter variation as you left the room. But I stayed, I remained, and I harvested the results, right? And I presented them to you yesterday. Ladies and gentlemen, there, as in calibration, we're having a situation where an experiment is running the model many times with different assumptions about parameter values. Just as in parameter variation, a lot of our interest lies in not just running with a given set of parameters, a given assignment of parameters once, but several times, replications, because of stochastics. We run the model several times for a given assignment of parameter values. So it is with calibration as well. And in fact, the general structure of how you specify these things is quite similar. Do you remember with our previous model, with our model before, that you, in yonder room, created this varying parameters here? Do you remember we put in these Java actions? Perhaps they induced a measure of distress. Do you remember this? We zeroed out the histograms. Remember we had a histogram 2D and a histogram? We reset them, and then every time we ran the model, we salvaged some data from it. We sucked out the data, like the fractional prevalence of smoking statistic, and we added it to our histogram. And we also sucked out a data set involving the fractional prevalence over time, and we added that. Remember that? And it sort of etched out, what it would do. Do you remember here? I'll go and show you. You probably remember this. Do you remember this sort of situation I showed you yesterday? And we had. Okay, I don't know why this is exhibiting. There it is. Remember this? Yeah. So that's indicative of the fact that we are running this model, and each time we're running it, we're grabbing some value out of it. Similar thing is occurring here with calibration. We're running the model over and over again in calibration, and just as we had these Java actions here, we're going to have Java actions down here, which are going to make use of the information. So there's going to be some things to do at first. We're going to reset some things. After each simulation run, we're going to salvage some data from there. Among other things, how did it do? Or, what was the profile of it? And we're going to ask, okay, is this the best iteration we've seen before? And if so, get that information.
Excuse me.
Yeah.
Is it just a simple grid search that goes in every combination, or we can have...
No, it's not. It's an adaptive process based on genetic algorithms. So it's based on a product which is quite popular and used by other simulation products or simulation systems, and it's called OpQuest. And if you look for OpQuest, it's used by Arena and Simulate, I think. Here, OpQuest optimization, and you'll find online information about this and something about the algorithms that they use. But it's very widely used outside of the context of AnyLogic. AnyLogic is one of their customers that provides that uses this for their software. Okay. Okay. So, ladies and gentlemen, let's look a little bit more detailed though how this occurs, because there's a bit more texture here. Here we're asking, is this iteration the best iteration? One of the key differentiators of this from the parameter variation is here we're not conducting just a grid search. We're not just conducting a one or multi-way systematic exploration in a fixed way. We're in fact engaged in an adaptive search which takes into account what of the best solutions seen thus far. I think it tries to combine some of those best solutions per this notion of a genetic algorithm, and tries to explore and identify where are the best places in the space as far as parameter values. And a key overriding thing here is this objective function. See this? It says objective. That's basically the discrepancy function. Here we are trying to determine how good, or in this case how bad, our match is for a given run to the historic data. So here's the historic data. This is a data set, ladies and gentlemen. It's a data set that we populate at the beginning of the run from historic data. So this is a table function. Just gives some historic data. DS infectious current, if you were to look it up, here it is in the function area here. Infectious historic, here's the historic data. Okay? What happens is that with calibration, it takes that data, puts it into a data set. And by virtue of putting it into a data set, every time it runs the simulation, it's going to read a data set out of, does anyone remember what root is? What is root? After each simulation run, we're doing what? What is root? Well, I'll remind you that not 2 days thence, you actually wrote the word root yourself in this context. Right here, you wrote it twice. What is root? What is it? What is the structure from which we are rescuing the data, like the fractional prevalence? Sorry? Yeah, it's main. This is main. This is where the population lives. This is where there's a data set in main. So root refers to main here, okay? And in the calibration context, so it is. So if we go back to calibration here, after each simulation one, we are reading from main the number of infectious cases over time, and we're putting them into our infectious cases. And why are we doing this? Why are we remembering this away? Because main is about to disappear. Remember that? Main disappears. It runs main many times. Main comes, main runs, we rescue some information from it, and it goes vamoosh. It disappears. Okay? So we're rescuing this information, putting it in a data set, and then that's the information that we compare against the historic data. Because remember, the historic data is showing the number of infectious cases over time, and we want to compare the number of infectious cases over time from the model with this, right? So that's why we're reading that out, ladies and gentlemen, out of the model here, out of the main, and we're saving it away here in a data set within the experiment, which lasts longer than the model. And from that, we're comparing what did the model think should be the number of cases over time versus what was observed historically. And we're trying to find the best match. So we're trying to minimize this objective function. We're trying to minimize this value to make the two as close as possible, to make the model match the historic data as closely as possible. And that's exactly what's occurring here. It's trying to max, right? And oh my gosh, it's still running. It's over 500. Okay. Wow. Okay. That's interesting. I thought we told it to stop at 500. Number of iterations 500. Well, I'll be okay.
So that means
yeah.
that historical data, you don't actually use it at all to inform the model. It's just there for your calibration.
This historic data is an emergent. It corresponds to endogenous behavior of the model, right? So this number of people who are infective over time, what does that result from in this model? Well, it results from an entangling of a bunch of factors, or from how long they stay infectious, for their contact patterns, their transmission probability given contact, who they're connected with. There's a lot of features of the underlying model that shape, and in fact the underlying system in the world, that end up shaping these sort of patterns. So we can't just put this into the model. We haven't used this to build the model previously. Instead, what we're doing is we have this data about how things behave in the world. We have this theory in the form of a model as to how that works. And we don't have the luxury of simply putting this into the model and saying, do this, make this happen. After all, we're interested in models more general than that. We're interested in models we can have counterfactuals about. But we need to have a theory that passes the red face test, that at least has face plausibility in terms of matching that data. Does that guarantee that the model's theory is correct? By no means. But it helps suggest that there's not glaring flaws in that model when it comes to accounting for at least this empirical data. Remember that models are learning tools. They're tools that help us learn more quickly, more deeply, more reliably, and they help us more quickly identify inconsistencies between what we think might be going on in the world and what is. And one of the earliest places this comes out in the modeling process is you try to calibrate and it just won't calibrate. It just won't jive with the empirical data. It just doesn't obtain a match with the empirical data. That's telling us something. That's not a failure of the model. It's a success of a learning opportunity if we can take advantage of it. Because we find in our theory, we had a cherished hope perhaps that it would match this data really well, but it just doesn't fit. It can't account for it. And so there we may say that we have falsified our theory or sort of successfully challenged it, and now it forces us to think about other possible, extensions or modifications of that theory, right? So that's what's going on. You know, we don't have the luxury. Thanks so much, Joanne, of putting this in. Thanks a ton. We instead are trying to match model output because this corresponds to endogenous features of the model, and we're trying to develop confidence as to whether our model or our theory does match things in the world. And this is one of the earliest places we find there's an inconsistency, right? Okay, so I see that the meals are here, and the morning tea is here. I'll just point out one other thing. So this other model that I have, that I prepared for you, this model has a similar structure, but it actually uses not just one data set. It's not matching to just one data set. It's actually matching a set. Okay? A set of sorry?
A set of sets?
Well, it's not just matching one observable. It's matching two observables.
Okay.
See? It's matching the current prevalence of infection as well as incident cases of infection over time. Okay? So it's trying to match both of these data sets at the same time, which is quite common that we try to match several different things. And often that's where the tension comes. We end up finding it matches really well to one, but to match one, we can't match the other. And there's a lesson there about why it can't match the other. We have to do experimentation and figure out what is it that's the challenge. What is it that doesn't jibe in our theory for why it can match both? And that provides that key learning opportunity in many cases to build a better model, to build a better theory in our head. Okay? So why don't we take the break now? And we'll come back in 20 minutes. I'll make some wrap-up comments on the calibration side, and then we'll move on to an additional topic. Thanks, before lunch. And meanwhile, I'm going to run this. So I have a theory, I have a hypothesis as to what's going on here. It said to stop after 500. I suspect, actually, I didn't realize that, maybe I forgot it, but this numbering, this may be the number of realizations it's run. And maybe we're dealing with 500 times 5, 500 iterations, so 500 different particular values of the two parameters that it's trying, and for each of them it's running five replications. Hence, I hypothesize this is going to go to 2,500. And by running it, we shall soon see. Okay? Thank you very much.